Hello again. Now in this session, I want to derive the momentum equation for shallow waters. So this is kind of the second shallow water equation in addition to the continuity equation that we derived for these flows in the previous session. Okay, so again, because this is a two-dimensional flow, I am going to only write the equation, the shallow water equations for the x component here, because that's the kind of the most important one. And also we have homogeneity in the y direction, meaning that in the span-wise direction everything is homogeneous. So I'm not gonna write the momentum equation in that direction. So let's get started. Write the x component of the Euler's equation. So I start with the Euler's equation, but only the x component of that. So we have du over dt equals to partial u over partial t plus u partial u over partial x. So velocity dot grad of u, right, plus v partial u over partial y plus w partial u over partial z equals to minus 1 over rho partial p over partial x. So this is the Euler's equation, and we assume, because this is in the x direction, we don't have gravity, right? So the gravity does not affect in the x direction, so I don't have it. And now, because we can do some simplifications, again we have homogeneity in the y direction, so I can just assume this term is 0, and also the velocity in the span-wise direction is 0. And so instead of doing that, I'm going to do it later. So let me just also write the continuity equation again for an incompressible flow, which is what we have here, water. So based on that, we have partial u over partial x. This is the continuity for an incompressible flow. Partial v over partial y plus partial w over partial z equals to 0. So I am going to multiply this everything by u. So what I'm going to get is u partial u over partial x plus u partial v partial y plus u partial w over partial z equals to 0. So I get this from continuity. And so I can just add this to the x momentum equation. So what are we going to get? So let me write it down. So the first term is partial u over partial t. The second term, we have 2u partial u over partial x, which equals to what? Equals to partial u square over partial x. You can take the take the derivative of this u square, and this is going to be exactly this. So I'm just going to write it down, partial u squared over partial x. And then we have u partial v. So we have u partial v partial y plus v partial u over partial y. So this means we have partial uv. Again, you can take the derivative of this and make sure this is equal, this is consistent. Partial uv over partial y. And similarly, for this second term, we're going to have partial uw over partial z equals to minus 1 rho partial p partial x. So again, we can assume this is 0 because we assumed homogeneity in y direction, and this means that when you assume this, it means that the derivative of any quantity in the y direction should be 0. Doesn't matter any quantity because we assume that we have homogeneous flow in the y direction, so the derivative of that should be 0 in the y direction. Okay. So now what I want to do, I want to integrate this equation, the remaining equation, from bottom surface to free surface. So from bottom of the flow to the surface, or from z to h. So let's get started. So first we have the integral from 0 to h of partial u over partial t plus partial u squared over partial x dz plus, what is the integral of the second term? So the second term, if you take the integral with respect to z, it's just going to be uw, right? So it's going to be uw from 0 to h equals to minus 1 rho. I can take it out of the integral because it's a constant. Integral from 0 to h of partial p over partial x dz. And this term, we know that the velocity at the wall is 0. So it's just going to be wh because uw at 0 is just 0, right? The velocity at the wall is 0. It's the no slip condition. Okay. So now, what I'm going to do is for the first term, I'm going to use Leibniz rule. So use Leibniz rule, integral rule, to bring the differentiation out of the integral. Okay, so let's see what was the Leibniz rule. We have it, I think. Yep, it's here. So I'm gonna put it here and then do it and then just clean it. Okay, so let's say for the integral from 0 to h of partial u over partial t dz, I want to use this. So this is gonna be just here, right? We have it here. So look how I'm going to write it. So f here is just u. So I have plus u at h, right? Partial b over partial z, so it's going to be partial, and z is just here is time, so it's going to be partial h partial t minus u at the bottom, which is just 0, partial 0 over partial t, again doesn't matter, this is just 0 because u at 0 is 0, equals to the left-hand side, z is again time here, so it's going to be partial over partial t of 0 to h of what? Of u, and x is z here, so it's going to be dz. Okay, so now instead of this, I'm going to use this Leibniz rule. So here we have this equation, so I'm going to write it as d partial over partial t of the integral from 0 to h u dz minus this term, which is uh partial h over partial t. This is the first term. And we can similarly use the Leibniz rule for this second term, for this term here. Okay, so I'm just gonna write the answer after using the Leibniz rule, but you can do it yourself. So it's gonna be partial over partial x of the integral from 0 to h u square dz minus uh square partial h over partial x. And these are just going to be the first two terms. And then we have plus uhwh plus uhwh equals to minus 1 rho the integral from 0 to h partial p over partial x dz. Okay. So let me put this here. Put these here. Okay. So what is this? Do you remember this? We defined it here. We made a definition. Let's look at it. This is just average velocity, right? Just compare these two. So it's just average velocity times h. So I can just write it down. So this is just u bar times h. And then the whole thing is gonna be partial u bar h partial t. Okay. And so what we have is as follows, is partial u bar h over partial t plus partial over partial x of the integral from 0 to h u square dz minus, and then I'm going to factor out uh here, which will lead to, so what do we have here? The first term, let me just make sure we have this. So it's going to be partial h over partial t, and then we have this term is going to be plus uh partial h over partial x, and then we have this term minus wh equals to minus 1 rho, the integral from 0 to h partial p partial x dz. Okay, and let's see what is this term. So let's look at our top boundary condition. So this is our top boundary condition that we set in the flow, which essentially means that dH over dt equals to WH. Right? This is what it essentially means. So let me copy it here, and then you take a look at it. So you just see that this is going to be what? It's going to be 0 based on this equation. So from 2 top boundary condition, this is going to be 0. Okay. So this term cancels out, and now I define velocity shape factor as follows. Velocity shape factor. I define it as Kc this is just a definition, remember. It's 1 over h u bar square, the integral from 0 to h u square dz, because I want to simplify this term. Okay, so when u, or the velocity, is z independent, is independent of z, independent of z, what does that mean? That means that I can take this u out of the integral, right? And this is gonna give me u square over u square times h, right? So you can take that out of the integral because that is not dependent on h, on z, and then you will just have times z from h to 0, so it's going to give me h, and thus c is going to be 1, right? In other words, here, say we have a channel, right? We have a channel here. If this u does not differ in different elevations, then this Kc is going to be 1. Like if you have this flow, say you have this water flow here, and this is the bed of the channel. If your u is just constant, is not varying with depth, it's constant everywhere, which is essentially not true, but like approximately you can say it is constant. I will put it here. Then u equals to u bar based on what we have defined, and Kc equals to 1. Okay. Also, in most of the applications that we do, and when the velocity difference from its average is less than 20%, the difference of the velocity from its average is less than 20%, then Kc will only change from 1 only about 4%. Meaning, say if your velocity, and you can look at it here, you can put it here and then get this, but meaning that if your velocity is like something like this, say, your velocity component is something like this. Let me extend this a little bit. So here, say your u bar, the velocity, the average velocity is going to be somewhere here, say. This is like here, u bar. So if this u minus u bar over u bar is only about 20%, this is about 20%, okay, then your Kc is only going to change about 4%. Okay, so the changes of Kc is very lower than this difference between the u and its average velocity. So in general, in our applications, we can assume that Kc is about 1. So we can assume in our analysis that this Kc is about 1. Okay, so if Kc is about 1, then that means that I can write, let me just copy this. Then I can write the integral from 0 to h of u squared dz equals to, approximately equals to, h u bar square. And so now I have these equations. Let me substitute that there to see what we get. So we have this equation. So this is just 0 based on what we learned. This equals to this, right? And again, this equals to h u bar square. So I can write it as follows. I can just remove this and write it as u bar square h so partial this partial x equals to this, the right hand side. Okay, so finally I'm going to use Leibniz rule for this, the last right hand side term, partial h partial p over partial x dz, Leibniz rule. So we are going to get partial over partial x of the integral from 0 to h p dz minus p at h partial h partial z plus p at 0 partial z over partial z. So this is just 0 with partial z over partial partial 0 over partial z is 0. And this one is also 0 because we have atmospheric pressure. And this is in terms of gauge pressure. And so we only have this term. And here, I can just assume that we have a hydrostatic balance. Okay. So for pressure, I can assume we have a hydrostatic balance. So let's say this is H. So at the bottom, this is going to be how the pressure looks like. So this is H, this is 0, and this is the hydrostatic balance. So P at H is going to be rho GH, right? This is the hydrostatic balance. So I can lose hydrostatic balance. So now I want to calculate this integral. So the integral of 0 to h of P dz equals to. So I'm going to just calculate the area of this, because this is what integral means. So I can just calculate this area. Which is going to be 1/2. This is just a triangle of rho GH times h. So area of triangle. So the term -1 over rho of partial 0h 0 to h of partial p over partial x dz just equals to -1 rho partial over partial x of 1/2 rho gh squared. So rho's, because rho is constant here, just cancels out. So rho cancels out. So I will have, and g is a constant, so I can take it out of the integral. So I have -1/2 g square root partial h squared over partial x. And so this gives me the final form of the final form of the momentum equation. So let me write it down in the next page. The simplified form of the momentum equation. So I'm going to get it here. I write it here. So it's going to give me partial u bar h over partial t plus this term partial u bar squared h over partial x equals to the right hand side, which is -1/2 g partial h squared over partial x. And this is what This is my momentum equation. In shallow water momentum equation, okay? And now if we add the continuity equation that we derived, we get a system of partial differential equations so that we can solve numerically. So this is continuity equation. And these two equations are known as shallow water equations. Shallow water equations in conservative form. So these are just simplified shallow water equations from momentum and continuity equation, and everything is now rewritten in terms of h, the depth of the flow, and the average velocity, the depth's average velocity. And so your only unknown here are what are h and u bar, or h times or u bar h. And these are conserved variables. That's why we call this in the conservative form. Okay, so you have these two unknowns, and you can just simply solve these two PDEs together to get u bar and h at each time, given the initial and boundary condition of your problem. Okay. So now I want to show an alternative form of this, which is kind of a little bit simpler form of it, not in the conservative form. It's an alternative form that you can also use. So for u bar, we have u bar. I can just expand these terms. So the first term is going to be u bar partial h over partial t plus h partial u bar over partial t. And then I'm going to expand the second term. So first is u bar partial h u bar over partial x plus h u bar partial u bar over partial x. So I'm just expanding this term equals to, and then I take the derivative of that, so it's going to be minus 1/2 g times 2h times partial h over partial x. Okay, so these 2's are canceling out. And now I factor u bar, so it gives me partial h over partial t plus partial h u bar over partial x plus h partial u bar over partial t plus h u bar partial u bar over partial x equals to minus gh partial h over partial x. And look here, what is this? From continuity, this is just 0. This is just continuity equation. So this term is 0, and among the remaining terms, h is going to cancel out because it's is in all the terms. So I'm going to get the alternative form of that, which is partial u bar over partial t plus u bar, partial u bar over partial x equals to minus g partial h over partial x. This is alternative form of the shallow water momentum equation. It's simply just a momentum equation, but for a shallow water case with the hydrostatic balance. Okay. So let me briefly review what we did in this lecture. So we derived the shallow water equations. So we started with the so these shallow waters again are valid for fluids in coastal regions, rivers, and channels where the depth of the flow is much smaller than the length of the flow. So we started with the continuity equation for an incompressible flow, so which is this equation. And then we integrated from 0 to h. We use the Leibniz rule. We define the average velocity as this, u bar. We use the top boundary condition, which is the bottom boundary condition. So the bottom boundary condition is no slip condition. And then the top boundary condition, which is this, the h over dt is just wh, meaning w at h. So don't confuse it here. This means w at h. It doesn't mean partial w over partial h. This is, don't confuse it with that. And then, after doing all these algebra, we finally get to our continuity equation, which is shown here for shallow waters. Similarly, for momentum equation, we write the x component of the Euler's equation. We do some algebra by assuming homogeneity in the y direction using Leibniz rule. We finally get here. And then also the top boundary condition, this term is going to be 0. And then we define the velocity shape factor as this. And we assume that Kc is about 1 in our cases, in our analysis, to be able to write the velocity shape factor in terms of u bar. We use the Leibniz rule and hydrostatic balance for the pressure term. And finally get this for the pressure, the forces. And so these will constitute our shallow water equations for the momentum and continuity equation for shallow water equations, okay? And then I found another alternative form of the shallow water momentum equation by just setting the continuity to 0 and getting it from our equation, momentum equation. And this is an alternative form of a shallow water momentum equation. Okay, so in the next lecture, we are going to talk a little bit more about these equations, trying to find some more insights about the dynamics of these type of flows.